Okay, this session is now being recorded. This is session number 3, right? Monday, August 29th. The first thing that we're going to discuss is quiz number 1. So overall, you guys did a great job working on these problems. And I did let my other class know that problem 3 is a little involved, but you handle it really well. So good for you. So a couple of comments I have about these problems. So we'll go through each one of them. Now, you also should get feedback from me. So now when you go to my grades, for quiz 1, you should see like a little bubble on Blackboard. And when you click on that, you should get my feedback. So everybody got an individual feedback for these assignments. Okay, so quiz number 1, problem 1. Here I ask you to determine equation of x in terms of y, right? So this is x as a function of y. And a couple of you emailed me asking if that means x is equal to da da da. The answer is yes, right? That's the terminology. So x is a function of y. This is the equation that I was looking for. Okay, and I ask for sketch and orientation and overall great solutions. A couple of things that I do want to point out. First, x as a function of y, right? Not the other way around. Okay, so that was specified. A couple of students missed orientation, so make sure that's there. So here on this graph, you can see how my curve is kind of starts on the bottom of the branch and goes up and then to the right. Okay, and I also pointed some values of t. Okay, you notice that this is not necessarily a super detailed graph, just a sketch, that's good. Okay, and you can use Desmos to check your work. But more importantly, when you rewrite your equation in terms of x or y, what some students missed is this. Okay, so this inequality right here. Now, some of you wrote it in a table, so that's completely great. So if you wrote it in a table that y goes from -8 to 12, I just made a comment, hey, make an explicit inequality that that's what that is. That's part of your equation. Okay, but we do want to emphasize that we don't get a full parabola, right? That's not an infinite graph that we get. We get this finite length curve. Okay, so that's the only thing that I saw that kind of was a common step that was missed. Okay. Now let's see, I'm going to go through all solutions and then we'll pause and discuss it one by one. Problem 2 was good, no issues here. Um, if you wanted, you could make a quick sketch of this curve and you see that this is an ellipse, right? Because we have two different values of the coefficient in front of cosine and sine. Okay, we compute our derivative and it turns out that it's 0 for t is equal to pi over 2. Okay, and since we're at pi over 2, we're at the point 0.8. That makes sense because we have a horizontal tangent line there. So the equation of the line, in this case, will be just y is equal to 8. And some of you wrote out the steps, how you computed it. That's great. Okay, or you can just say, yeah, oh, yeah, this is a horizontal line at the point 0.8. So y is equal to 8. That is the answer that I was looking for. So overall, good job here. And then problem 3, so this one was a little bit more involved than the others. Okay, this problem is directly through from your textbook actually. Um, I picked it up there. I don't think it has the answer key. I'm not sure. It might have the answer key. But anyway, I'm giving you a full detailed solution here. So we're applying this formula for area under the parametric curve. Okay, and the first step that we need to do is carefully multiply that through, multiply this integrand. So that's where a couple of mistakes here happened here. Okay, when you multiply this through, we get two quadratic terms, right? Okay, and then that middle term. Now I pulled out the -3 for the entire integral, right? So if you didn't, you got -6 sine t sine 3t, right? So I was looking for that term. That is part of the solution. Okay, and I wanted to see how you handled integrating this part. Okay, so if you missed that part, you know who you are. Just make sure you go back and carefully multiply this through, FOIL it, combine like terms. Okay, we know how to handle quadratics. So here I am kind of splitting it up in three integrals to show you how I've done my calculations. Now, most of you just did it all in one step, which is fine, no problem. So I broke it down, and for my first one, I got 3 pi over 2. For the third one, that's also double angle, I got negative pi over 2. And the middle term, so many of you recognize that this is product to sum, which is great. It was awesome to see that. So product to sum formula, which makes this computation very simple, right? Now we have cosine 2t minus cosine 4t. We know how to integrate it. And it turns out the whole thing vanishes, right? So the whole integral is 0, okay? But I was looking for that portion right there. Was that step included in your solution? Once we combine all of it, okay, I accepted for full credit the answer negative 3 pi because we haven't discussed what happens if we get negative, right? So we got a negative in this case. Why did we get that? We got it because if you actually trace that curve, if you graph the curve, oh, it's not listed in here in the solution. We see that it's the x is going in the negative direction. It goes in the opposite direction. Okay, so we get a negative, which again, I didn't really mention that in my lecture, so it's not a big deal, and I did not expect you to address it, but some of you did, which is amazing. So full answer, full credit was awarded if you just got negative 3 pi. That was good too. Okay, so this is your quiz. Okay, and that's what we're gonna do every week. So your handwritten solutions, right? Put your absolute best effort into it. Imagine, this is kind of like your mini take home. You can use anything you want as far as like help. You can ask for questions. You can discuss it with each other. You can use graphing utilities. It's open book, open notes. But that's what we're going to have every week. Okay. All right. Let me pause right here. And if you have any questions about any of these problems, this would be a good time to address them. No questions? All good? All right. If you come up with a question some other time about it, okay, definitely let me know. All right. So now that we are done with this, nope, that's not. I don't want to rate this. What are we doing? We are going to discuss polar coordinates and curves. Okay, so that's what we will be doing today. And then next session, we will be talking about calculus of polar coordinates and curves. Okay, and then what's going to happen next week? We're not meeting on Monday. Do you guys know why? There's no meeting on Monday. We will have, yeah, Labor Day? Labor Day, yes. Okay. I always do Memorial Day or Labor Day. Which one is which, right? So Labor Day is on Sunday, so Monday is a national holiday. We will not have a session on that day. We will have session on Wednesday, which means we'll have a very packed session. We have to cover a lot of stuff during that time. Okay, so take the time to relax on Monday and then come back in on Wednesday, ready to tackle vectors, right? So we're going to talk about basic vector operations, okay? But today we'll talk about polar coordinates and curves. So let's go ahead and talk about the first section of this topic. And what I'm going to start with, graphing a point with coordinates 1, 3. So let's say I have a point with coordinates 1, 3. Okay. I know how to graph it. It's 1 for x and 3 for y, right? So let's say over here, this is 3 for y. Okay, so here my point 1, 3, and that's one way to represent this object, right? So think about it, this is an object in a plane, okay? Is there another way to represent that object? Okay, well, this is what we call rectangular coordinates. And why do we call them rectangular? It's because if you were to project these coordinates onto the corresponding axis, right? So 1 onto x and 3 onto y, we get a rectangle. Okay. Now, is there another way to represent that same object? Okay. And the answer is yes. So I'm going to go ahead and sketch this same point P. Okay. And now I'm going to think about it in a slightly different way. Instead of saying, okay, how do I get to that point? Well, I go 1 to the right and 3 up, right? So that's kind of one way to say it. From the origin, I go 1 unit to the right and 3 steps up, okay? Instead, we can say, okay, I'm going to go this distance right here, whatever this distance is. And I'm going to go at this particular angle, theta, okay? So the distance, we're going to call it r, which stands kind of like for radius, right? So another way to describe this point would be to give the distance, or r, from the origin and the angle that that line segment forms with the positive x-axis, okay? So r theta. And that's going to be the way for us to represent these points in polar coordinates, okay? Polar coordinates, polar, think about it as a circle, right? Now imagine you were to just take this radius, right? And just trace it all around, okay? From angle to 0 to 2 pi. We get a full circle, right? So let's see if we can find a relation between the regular rectangular coordinates and our new way of representing this point. Okay, so let's go ahead and take a look at this triangle right here. This is a right triangle, okay, where we have r, which is the hypotenuse, and this is our x and this is our y, right? Those are the coordinates. So one of the first relations that we can establish right away is that r squared is equal to x squared plus y squared. Okay, and that is just our Pythagorean theorem, right? Pythagorean theorem says that the square of the hypotenuse is equal to the sum of the squares of the legs, and that's exactly what we have here. So that's one of the equations that we need to remember when we're going from one system to another. Now let's see, what else can we do here? Well, we have this angle theta, right? So angle theta, okay, we can define tangent of theta. Tangent of theta is what in this case? Well, let's see. Tangent is the opposite leg over adjacent, right? So that in this case would be y over x. Okay, so tangent of theta is y over x. Again, this is nothing brand new. We're just kind of recovering this information from pre-calculus, right? But in a slightly different setting, okay? So what else can we say from here? Okay, let's talk about sine and cosine of this angle. Okay, if I wanted to find sine of theta, okay, sine of theta is opposite over hypotenuse, right? So this is y over r. So from here, I know that y is equal to r sine of theta. And similarly, in exactly the same way, we can determine what x is. X is equal to r cosine theta. Okay, so these are the fundamental equations that we will need to remember once we are ready to go from one system to another. Okay, So we haven't done anything with points just yet. Okay, but let me pause here for a second. Is this okay? Do you guys remember these basic trig identities and how we define trig functions through a right triangle? Okay, I see a thumbs up from Carmen. Good. All right, excellent. Okay, then what I'm going to do now, I'm going to pick some points and we're going to plot them on this plane right here. Okay, so now our polar plane is no longer going to be rectangular. We need radius or we need angle. All right, so let's go ahead and start with some points. My first point A is going to be 2 for r pi over 6 for theta. Okay, so what am I doing? Okay, I'm going to find my angle pi over 6. Pi over 6 is what? It's 30 degrees, right? So let me go ahead and mark it here. This is my pi over 6. Okay, so that means this is where I am on this branch right here. And I go all the way to R2. So that's where I stop, right? So this is my point A with polar coordinates radius 2, angle pi over 6. Okay, let me go ahead and make this line segment right here to represent that radius. Okay, so that's my first point. Let's go ahead and graph a bunch. Okay, so next one is 3 pi over 4. My point B has the following coordinates. 3 for radius, 3 pi over 4 for the angle. So 3 pi over 4. Where is that angle? Do you guys remember how to find it? So in degrees, how much is it? So quadrant 2, okay, you can think about it as we're going to go by pi over 4, right? This is how I think about it. 1 pi over 4, 2 pi over 4, 3 pi over 4. Okay, so this is 3 pi over 4. Okay, yes, quadrant 2. And we're going to go 3 for radius. So 1, 2, 3, right here. Okay, that's my point B. Okay, let's do point C. And this one will have coordinates 4, negative pi over 2. Okay, we can do this. There's nothing wrong with negative pi over 2. Okay, negative pi over 2, we're going to go clockwise, right? So going from 0. So this is equivalent to the angle 3 pi over 2. Okay, and then radius is 4. So where am I? 1, 2, 3, 4, right here. That's going to be my point C. Okay, so far we've dealt with positive and negative angles, but you've noticed that the distance r is always positive. It doesn't have to be. It can in fact be negative. So let me go ahead and give you a couple of points where r is negative and how we deal with them. So let's say I have the following. D is negative 5 for r, 7 pi over 6 for theta. Okay, how to graph this? This is actually pretty simple. So what we're going to do, we're going to pretend that there's no negative there for our r. Okay, there's just 5, 7 pi over 6. Okay, so 7 pi over 6, where is that? That's an angle in which quadrant? It's third quadrant, right? Okay, so it's 210 degrees. So imagine there's no negative there, and I'm just going to do 5. So step number 1, just graph 5, 7 pi over 6. That's what we're going to do first. Okay, so 1, 2, 3, 4, 5. This one right here. That's not our point just yet. Okay, that's 5, 7 pi over 6. We want negative 5. So what we're going to do now, we're going to project this across the origin. So I'm going to go all the way to the origin and keep going until I hit 5. So that would be over here, right? Same distance. 5 is right here. So that is my point D. Okay, that's negative 5, 7 pi over 6. Okay, or what's an alternative way of writing this that same point? Can somebody tell me? Do you guys see it on the graph? So one way is negative 5, 7 pi over 6. What's another way? If I were to make this 5, what would be the angle? 5 pi over 6. Very good. Okay, yes. All right. So one of the problems on your homework will be of the following format. Here's a point. Determine two different representations of it. So that's what they're asking you to do. Okay, and you'll get a couple of multiple options. So you'll select the one that's correct. All right. Let's go ahead and do one more of this same type. E, let's call this point E, negative 6 pi over 3. Okay, so where does this point live? Pi over 3, that's 60 degrees, right? Okay, so we're going to pretend that negative is not there, and we're just going to plot 6 pi over 3, so this point right here. And now I'm going to go across through the origin, and I'm going to keep going through here. Okay, so that is my point E with coordinates negative 6 pi over 3. Okay. All right. So this is how we would graph points in a polar plane. Okay. Take a look at these solutions. Let me know if there's anything you'd like to discuss. What do you guys think? All good? Is this familiar? Have you guys done anything with polar coordinates, or is this mostly brand new? No wrong answer, remember. I'm just curious where the class stands. Okay, so most of it is brand new. Looks like it's a little bit familiar to Carmen. Okay, that's all right. We're going to take our time with this particular topic. I used to just cover both parametric and polar curves in 1 week, and now I'm spreading it out a little bit because I think that time is needed. So we're going to do a lot this unit, then we're going to kind of forget about it for a little bit. And then we'll come back to it again when we're ready to integrate things. But polar coordinates are a good, nice way for us to rewrite curves and points. And the good news is integration is really easy. It makes your integration much simpler in many, many cases. So if you're a little intimidated by it now, don't be. This will become a lot easier with practice. Okay, so let's go ahead and take a look at a couple of examples where I want to convert from one system to another and adjust the point, and then we'll talk about equations as well, how to convert equations. Okay, so let's say I have this point in rectangular coordinates, 0, negative 4, right? And we can actually sketch it. This is nothing too complicated. I'm going to go ahead and sketch that point. 0, negative 4 sits right here, right? 0, negative 4. Okay, so just by looking at the graph, okay, by looking at the graph, can you guys tell me what the polar coordinates are for this point just by looking at the graph? And there's more than one answer to this. Okay, so polar coordinates of A. So r is equal to something. R is equal to 4 and theta is 3 pi over 2. Okay, so that's what I see from Carmen. R is equal to 4. Theta is 3 pi over 2. That's correct. Now, Javier, if you were to do negative, then you would actually, for negative 4, right? You would end up over here. So this one right here would be negative 4, 3 pi over 2. And that's okay, right? We're just learning. We're learning just now how to graph these. Okay. But first we'll find. Oh, I'm sorry. No, yours is 3 pi over 2. Yeah. Do you see the difference? So this is a question for Javier. See the difference? Yeah? Okay, good. Okay. Again, remember, making mistakes in this class is encouraged. This is how we learn. All right. So by looking at the graph, you say, sure, I can figure it out. Okay. R is equal to 4, theta is 3 pi over 2. But how do we determine it if we can't just figure it out easily, right? Not all points are easily like this. Okay, so in this case, we would use our equations. So r squared is equal to x squared plus y squared. Now let me derive it for you. How would you go about this if you were to convert a point from rectangular to polar without it being this nice, right? Okay, so what do we do? R squared is equal to 0 squared plus negative 4 squared, right? I'm just plugging in my coordinates of that point A, okay, into this equation. And here I get R squared is equal to 16, okay? So technically R is equal to plus or minus 4, right? R is equal to plus or minus 4, but you can just pick one. And for the easy answer, we'll go with the positive, right? So we know that our R is going to be positive 4. Okay. Could you go with the negative? Yes, you could. Just like Javier tried to do this, right? So in this case, we would just have negative 4 pi over 2. Okay. But let's go with the simpler one. R is equal to 4. Okay. So now, how do we find that angle, though? Okay. We know that tangent of y over x is equal to what? Its tangent is negative 4 over 0. Ooh, I'm sorry, it's tangent of theta, right? So tangent of theta is equal to y over x, negative 4 over 0. That's undefined, right? And now you say, okay, where's our angle undefined? Well, where's tangent undefined? So theta is either pi over 2 or 3 pi over 2. Okay, so in which case you say, okay, well, which one do I pick? Well, it depends. Which R did you pick? If you picked the positive one, okay, R is positive, then we get the angle of 3 pi over 2, right? So since x is equal to 0 and y is equal to negative 4, we pick theta is equal to 3 pi over 2. So one way, right, one way to write our point would be r is equal to 4, theta is equal to 3 pi over 2. What's a second way? Okay, so second way would be what? What if I were to do negative 4, right? Then you could do theta is equal to pi over 2. Okay, which one is correct? Both of them are correct, right? Okay, there's several ways to write this point in polar coordinates. Okay, all right, let's see. Let's pause here for a second. Okay, do you guys have any questions? Anything you would like to discuss? Is this okay? Yes, excellent. All right. Let's go the other way. What if we have a point in polar coordinates and I'd like to convert it back into Cartesian? Okay. This one is actually a little bit simpler. Okay. We just need to remember the equations. Our equations are x is equal to r cosine theta, right? And y is equal to r sine theta. Okay. And if you ever forget, just put that red triangle back on the sketch, and then you'll be able to rederive these from that right triangle. Okay. Well, if that's the case, we know what our r and theta are. Okay. So r is 5, theta is negative 3 pi over 4. Okay. Let me go ahead and put a unit circle here. Let's see, negative 3 pi over 4. That would be 1, 2, 3 right here, right? This is our angle, negative 3 pi over 4. Okay, so we can now compute x and y coordinates. X is 5 times cosine of negative 3 pi over 4. Y is 5 times sine of negative 3 pi over 4. Okay. Um, in here, and this is unit circle, right? Both cosine and sine are negative, and they have the same value, square root of 2 over 2, right? So we get negative pi root 2 over 2 for this coordinate, and negative 5. Did I say pi? Negative 5 root 2 over 2, and negative 5 root 2 over 2 for the y. Okay, so our point B in regular rectangular coordinates is this. And again, this is a problem that I selected from your online homework. Okay, so it's asking you to plug in exact answers. Okay, so let me go ahead and make a note. Please do not approximate. Plug it in just like this. Otherwise, it's not going to give you credit for it, and then you'll have to go back and redo this problem. Okay, so do exactly like this. Okay. All right, so that's what exact answer will look like. All right, so some of those will ask you for different values of theta, right? So if you need to review your unit circle, that's something you might want to do, or you can just look it up on a table, right? So let's see. So these two ways, one going from polar to rectangular, another from rectangular to polar. Okay, all we got to remember are these fundamental equations. This one, and let me highlight the tangent one. Okay, those are good to remember, and maybe that's something you can add to your formula sheet as we're reviewing all the materials. Okay. All right, let me pause here for a moment. Take a look at this. And I know, so most of you are brand new with this, right? So this is, you've never seen this before. So it's okay to let your mind kind of absorb this and process this information. Okay. I do not expect you to just get it just like this, right? That's not the expectation. Take your time, working through these problems, and then it does get better. It does get easier. You get more comfortable with dealing with these curves. Okay, so I'm going to give you some time to take a look at it and let me know if there's any discussion that we should have about these. All right, I see a couple of thumbs up. Okay, so what we're going to do next, we're going to look at the curves, right? So we just briefly covered how to sketch points, okay? But really, we want to know how to sketch curves in polar coordinates, okay? So that's the big goal, to get comfortable with curves that are defined by polar coordinates, okay? And get a good idea of how to go back and forth. And again, for these next few sections, I urge you guys to use Desmos to graph all of your curves because it's a nice tool that really lets you visualize what's going on. Okay. So before we get into graphing, let's get really comfortable with just conversion and just get you comfortable with the whole idea that, oh, okay, now we have this whole new way of writing curves. Okay, so the next few examples will just ask us to do algebraic steps um, to go from one system to another. Okay, so let's take a look at this curve right here. Okay, it says R is equal to cotangent of theta times cosecant of theta. Okay, so what is the main goal here? The main goal is to rewrite in terms of x and y. And if you look at this curve just as is, I have no idea what that looks like. Okay, I do know because I've solved this problem, right? But if we were just to look at this, it's not clear what the curve is. Okay, but if we convert it into x and y, we might find out that it's a curve that we're very familiar with. Okay, so what am I going to do? I'm going to take my equation. So this is r is equal to cotangent theta times cosecant theta. Okay, and I'm going to try and rewrite all of this in terms of x and y. So the goal is to eliminate r and thetas and just have x and y. Okay. All right. So let's see. I remember this one of the things that we said, y is equal to r sine theta, right? This is one of our fundamental things. Okay, that's one of the fundamental equations that we need to use. All right. Now I also see that r is equal to this expression. So this is my r, right? Okay, so that's the equation that I'm going to start with. Y is equal to r, which now I'm going to replace that r with cotangent theta times cosecant theta times sine theta. Okay, so I just plugged this one in here. All right, let's see if we can do anything about this. Let's see, cotangent theta, cosecant theta times sine theta. Okay, so cotangent theta, cosecant theta is what? That's 1 over sine, right? So these two cancel out. And we just end up with what? Cotangent theta. And cotangent theta is just another way of writing x over y. Because remember, that's another equation here, that tangent theta is equal to y over x, which means cotangent theta is x over y. Okay, so you have now this equation, y is equal to x over y, and we can solve it even further for x. X is equal to y squared. Oh, we know exactly what that is. Okay, what is that? Now, in this case, this is a parabola that opens to the right, like this, right? Okay, that's x is equal to y squared. And we know exactly how to deal with this graph and how to sketch it, and we know all the properties of this curve. Okay, so that's the idea here, that we want to be comfortable going from one system to another. Okay, and again, a big goal, or kind of like keep that in mind. Why do we do this now? Okay, when it's time to compute integrals. Some of them are extremely complicated in Cartesian system. They're just messy and needy and really, really challenging. Unless you convert everything into polar coordinates, and then it becomes nice and simple and beautiful answers. Okay, because a lot of times it's just easier to do calculus in one system than another. Okay, so let me pause here for a moment. Here's your curve that we could graph, and I'm going to also show you how to graph it on Desmos. But let me know if there's any discussion, any questions, any confusion. Please do so. Is this okay? Am I still with you guys? Yeah. Okay. All right. I see a couple of thumbs up. Very good. Okay. So we have a whole bunch of problems of this kind that we're going to go through. And that's going to be your second assignment. The first assignment is more or less just like points and going from one system to another. The second one is all about equations. Okay, and the last one, the third one, will be about calculus. All right, so let's go ahead and take a look at this next equation. This one is r is equal to 3 cosecant theta. Okay, so what is that curve? Turns out this one is also pretty simple. So I'm going to go ahead and use the same equation I did last time. Y is equal to r sine theta. Okay, and as you work through these problems, you might not be able to figure it out which equation to use right off the bat. That's okay. That's the whole process, right? That's the whole learning. If something doesn't work out, okay, leave it be, and try it different, right? So sometimes you'll use y, sometimes you use x. It depends on what is given to you. So why am I using y is equal to r sine of theta? Okay, whenever there's this cosecant, right? I know cosecant is the reciprocal of sine. So which of the equations go with sine? The y. That's why I'm using y is equal to r sine theta. Okay, so now I'm going to substitute this for r. So this is 3 cosecant theta times sine theta. Again, this is just 3 times 1 over sine theta times sine theta. These two guys cancel out. Just get y is equal to 3. Oh, that's our straight line, right? So if I were to sketch it, it's just this horizontal line, y is equal to 3. And that's it. Okay, so even though it looks maybe a little intimidating, r is equal to 3 cosine theta, but it's not. It's just a straight line. Okay. All right, let's take a look at example number 3, and then we'll pause again to review all of this. So here I have this equation that says r is equal to 2 times sine of theta plus 2 times cosine of theta. Okay, now here I'm going to use a trick. That's just one of those methods to kind of keep in mind. I'm going to multiply each side by r. Multiply each side by r. Okay. Now, why do I want to do that? Remember, you want to convert everything in terms of x and y. I'm kind of missing that r in there, right? Because if I had 2r sine of theta, well, I know this is y, right? And 2 cosine of theta, that would be x, but I don't have it. So, but we can multiply it. So if I do that, I'm going to get r squared is equal to 2r sine theta plus 2r cosine theta. Okay. And now we have all of the components to rewrite this equation in terms of x and y only. Why? I know what r squared is. That's exactly Pythagorean theorem, right? That's x squared plus y squared. Okay. Equals to what? Here I have 2y plus 2x. Now, technically, this is an equation in terms of x and y, right? So technically we are finished, but we still don't really know what that object looks like. So what we're going to do, we're going to complete the square, and you will see that what we actually get a circle. Okay, so to complete the squared, I'm going to group up my terms, x's with x's and y's with y's, right? Here I'm going to get 0. This is still an equation. So what I just did, I just moved 2y and 2x on the other side of the equation. Okay. And let me remind you how we need to complete the squared. So I want to put something here, and y squared minus 2y something here, and then something also going to go on the other side, right? So what would be the perfect square for the first term? Excuse me. That would be x minus 1, right? So this would be 1 squared that goes over here, and 1 squared goes here. So we're adding 2 to the other side to keep the equation balanced. And now we can convert it back into this form right here, x minus 1 squared plus y minus 1 squared is equal to 2. And that equation does tell us what this curve is. Okay, this is a circle of radius root 2 cent at the point 1, 1, right? Okay, so this equation right here is the final answer that we're looking for, okay, because it gives us exactly the location and description of our circle. All right. Okay, so this is a good problem. I like to put a problem like this either on a quiz or on a exam, because it really tests a lot of your understanding here, right? So what's the way to convert, how to manipulate these terms to get back to our form, the Cartesian form that we're used to, and also recognizing what that object looks like. Okay, so example 2 and 3. Take a moment, take a look at this. Let me know if there's any discussions, any comments. Javier, tell me what that emoji means. What's going on? Are you overwhelmed? Give me a little bit of feedback. Are you guys are letting me hang here? You're surprised about what? Surprised about what?
Oh, I was just surprised that the R was the original function ended up becoming a circular function at the end.
Oh, okay, yeah, yeah. It's not clear, right?
Yeah.
I mean, yeah. So we're actually going to take a look at a whole bunch of curves and what they look like graphically. Okay. And yeah, so with these polar curves, it's really unclear what they're going to look like unless you graph it, and then it's like boom, there it is. And it's very usually they're nice and pretty and circular. And so that's one of the things keep in mind once you guys are ready to integrate things over circular regions. That's when we want to use polar coordinates. All right, let's take a look at the next example. Okay, so here, our last example to go from polar to Cartesian, and then we're gonna figure it out what do we do if we need to go the other way? Okay. All right. Let's take a look. What is this one? Here, I have r is equal to 1 over the sum, right? So let me take a look at these two examples to kind of put them back to back. One is just r is equal to the sum of two things, right? Another one is 1 over. The trick is the same, sort of. Is it the same? Well, no, not quite. Sorry, this is a different trick. We're going to multiply this by something, but not r. So what we're going to multiply this by the denominator. We're going to clear the denominator. So we're going to do 2 cosine theta plus 3 sine theta on one side, and then same on the other. No, let me move it over here. Okay, 2 cosine theta plus 3 sine theta here. Okay, now once that happens, here, numerator and denominator are gone. And what do we have left? I'm going to go ahead and distribute that r. So we're going to get 2r cosine theta plus 3r sine theta is equal to 1. Okay? But now you say, wait a minute, but that's just x and y, right? Okay. R cosine theta, that's x, r sine theta, that's y. So I have an equation in terms of x and y, 2x plus 3y is equal to 1. Okay, that's your standard form of a linear equation. You can keep it like this. This is completely fine, no problem. If you like to put it in the form y is equal to mx plus b, that's fine as well. So if you were to solve it for y, what do we get? We get y, so this is or, y is equal to negative 2/3 x plus 1 over 3, right? Okay, and now you say, oh, I know exactly what that line looks like. It's a line that goes through 0, 1 over 3 with the slope negative 2/3, right? We can give an explicit description of that object because we know how to go from polar to Cartesian form. Okay, so let's see what the tricks are here. Okay, so for the first two problems, we just need to kind of recognize which of the fundamental equations we should use to go from one system to another. And again, as I mentioned this already, if one of them doesn't quite work out, that's okay. Let it be, and then take the other one. Okay, and it will be kind of like a trial and error process to determine how to go from one way to another. Okay, then this nice trick to remember, multiply each side by r whenever you see this kind of like a missing thing, right? 2 sine theta. Ooh, wouldn't it be nice if we had r in there because then we can rewrite it in terms of x? Yes, we can do that, multiply by r on each side. Over here, we just cleared the denominator, and then turns out we get a nice line. All right, so that's the 4 examples that I'm prepared for you guys for going from polar curves to Cartesian. Okay, now let's go ahead and go the other way. Okay, now some of these should look familiar to you. So let's see, y is equal to x squared. We already know what that curve is going to look like in polar coordinates, right? We just worked with it a few examples above. But how would you approach it if you don't know, right? So what is the goal here? What is my goal? Okay, my goal is to rewrite as r is a function of theta, or sometimes it will be r squared is a function of theta. Okay, in some examples, we end up with having r squared, which is no problem. That's completely fine. Okay, so whenever you read a problem, just make that note. Okay, what is the main purpose here? Okay, if I'm going to polar coordinates, that means x and y need to be gone, and all I will have is an equation in terms of r and theta. Okay, I have y is equal to x squared here, right? That's what we got. So I know that x is equal to r cosine theta, and y is equal to r sine theta, right? So these are my fundamental equations. I'm working with this equation right here. So I'm just going to substitute. I have all my ingredients. I'm going to do the substitution. So I got r sine theta on the left is equal to r cosine theta squared on the right. Okay, and now let's just work with this equation. R sine theta is equal to r squared cosine squared theta. Now remember the goal. The goal is to write it in form r is equal to stuff, right? Okay, some stuff. So let's go ahead and solve for r. R is equal to, let's see, how do I want to do it? Yeah, let's do this. That's fine. Sorry, not r is equal to. We're going to do sine of theta is equal to r squared cosine squared theta over r. Okay, so this and this cancel out. And now we have sine theta is equal to r cosine squared theta. Okay, now we can solve for r. Let me go over here. R is equal to sine of theta over cosine squared theta. Okay, but what is that? So this is r is equal to sine theta over cosine theta times 1 over cosine theta. Okay, let's see. What's sine over cosine? We know that. That's tangent. And what's 1 over cosine? That's secant. Okay, so your final answer here is done. Now this should look similar, right? This should look similar to what we've done. We've computed the equation. They gave us what? X is equal to y squared. But if you look at it, these are all reciprocals, right? So the idea will be the same. Okay, over here we have y is equal to x squared, and we end up with r is equal to tangent theta secant theta. So once you have that equation, now you know what that parabola will be looking like as far as a polar curve. Okay, so your final answer, let me just put it over here, r is equal to tangent theta times secant theta. There's nothing else we can do here to simplify it. This is it. Okay. All right. Let's pause here for a moment. What do you guys think? What are you thinking so far of polar coordinates and curves in general? Good? Not too bad? Yes. I'm glad to hear all of this. Okay. Again, let your mind process this information throughout this week. Okay. It's all right if there is some confusion. That's okay. No problem. Okay. Let's see. What else do we have? We have a couple more problems to go from one form to another. Then we'll graph some curves, and I'll show you how to do it in Desmos. And then we're actually going to go ahead and start next section as well. I want to make sure that we spend enough time on areas because those problems get a little involved. So if we have time today, we'll definitely do that. Okay, let's see. Convert to polar form. Let's take a look at this example. All right. Let's discuss this problem right here before we even start converting it. Do you guys know what that object is? Can somebody tell me what is this object? If you, can you tell by just looking at that equation? Let me give you a reminder. It is a circle. Good. So it is a circle. Nice. Okay. What is the radius? The radius is 1. Very good. What about the center? 1, 0. Excellent. Okay, so we know exactly what that looks like. Very good. All right, so that follows that form right here, right? So I think we've discussed it last time. X minus x null squared plus y minus y null squared is equal to r squared, right? So from here, you can tell exactly what that object looks like. Okay, now let's go ahead and convert it. So how would I go about it? Okay, well, there's only one thing to do. We have x and y. We know what x and y are in terms of r and theta. So we're just going to substitute it. Okay, let's see. X is equal to r cosine theta minus 1 quantity squared plus y is equal to r sine theta, right? So r sine theta quantity squared is equal to 1. Okay, so now we just need to carefully multiply this through combine like terms and solve for either r or r squared. Okay, well, all right, let's see. What do we get here? This is r squared cosine squared theta minus double of the product, right? So that would be minus 2r cosine theta plus 1 squared, so that's 1, and then plus r squared sine squared theta, and all of that is equal to 1. Okay, so let's see what we can do here. I'm going to go ahead and combine these two. If I factor out r squared, I get sine squared theta plus cosine squared theta. And then here I get negative 2r cosine theta. And then this 1 and 1, they can also be canceled out, right? So what do we get here? 0 on this side. Okay, what is this expression? You guys know what that is, right? That's 1. Yes, that's our fundamental trig identity, right? Okay, very good. So we recognize that. So this is r squared minus 2r cosine theta is equal to 0. And we can move stuff to the other side and we can actually reduce it by r. So if you can reduce by r, you can do it. You can just cancel it out. Now let's say for the sake of argument, you just had r squared is equal to 2 cosine theta. Just keep it as is. You do not need to take our square root of r. Okay, now because we can cancel out r, we get a nice equation in terms of just r and theta. So 2 cosine theta, that's your final answer. Not cosine squared, just cosine, right? 2 cosine theta is equal to r. Okay. All right. So why don't we graph this? You told me, guys, that this is a circle of radius 1 centered at 1, 0. Okay, I'm going to go to Desmos here. Okay, and some of my curves are already kind of prepped. Okay, so how would I do this? I would just go like this. R is equal to what was it? 2 cosine theta, right? So 2, I'm going to go to function, cosine, and theta here. And we said that it's a circle of a radius 1, which that's what that is, centered at 1, 0. Yep, there it is, looking at you, right? So how would I come up with this plane? Let me go ahead and show you guys. When you go to Desmos, there's a whole bunch of things that are kind of built in already, that are preset for you. So I would go here, and some of these files are mine, so ignore that. But if you kind of scroll down here, and go alphabetically. You see those polar rows, polar logarithmic spiral, polar limmason. All of those will give you this preset plane already, because by default, the plane is just Cartesian. So just click any of those and delete all of the equations that are already there. Okay, and then you are set with your plane. Okay, so here's my polar plane, and it shows nicely all of those angles, right? The ones that are in radians. Okay, so we gave a description of this object. We showed algebraically that that's what that is. Yep. Okay. All right. So let me go back here to the notes. Let me pause here for a second. Okay. R is equal to 2 cosine theta. That's our final answer. Okay, do you guys have any question? Anything you would like to discuss? All right. Very good. Okay, then let's keep going. Last one. You guys want to try this one? What do you say about trying to convert this on your own? Excellent. Okay, so as long as one student is ready to do it, I'm all for it. Okay, why don't you guys go ahead and work on this on your own, and whenever you're ready, we'll compare the answers. And maybe we'll have one of you just fully explain your thought process. Okay, so looks like Carmen has an answer for us. Okay, that looks good. Carmen, you want to walk us through this? You can say no, but I want to give you an opportunity to discuss this.
Sure.
Go ahead. What'd you
I
do?
just first I plugged in for y r sine theta, and then for x I did r cosine theta. So r
Okay.
sine theta equals 1 over r cosine theta.
Okay, so that's our first step. All right, what'd you do next?
Then I just multiplied both sides by r cosine theta.
Okay, so that's r sine theta times r cosine theta is equal to 1. Okay.
And then I just took out r squared and
Hmm.
divided by sine and cosine theta.
Very nice. Okay, so that's one way to do it. And notice how she didn't take the square root, right? Very good. So you want to keep it as is. Or you could also rewrite it as secant theta times cosecant theta. Either one is fine. Both are correct. But let me fix that. That looks kind of ugly. Cosine theta on the bottom here. Okay, but we want to make sure we do not take the square root, right? Okay, so let's make a note here. Do not take square root here. Okay, r squared is equal to secant theta times cosecant theta or 1 over this product. Okay. All right. Yep. Very nice. Okay. We know what that function looks like, right? We know what that curve looks like. If you were to graph it in rectangular coordinates, um, this is a reciprocal function, right? So it's going to look something like this. Okay. But now you can also say, okay, I know what the description of that same curve is using polar coordinates. All right. Did you guys get this? The rest of the class? Yeah? Okay, very good. Okay, so before we do the graphing, what we've done so far, kind of a quick derivation of this whole idea of how to write things in polar coordinates, right? Okay, so then plotting points in a polar plane with different representations, and then these fundamental equations to keep in mind. Okay, then we talked about converting points, right? Just the points from one system to another. What do we do here? And then converting equations of curves. Okay, so rewrite them in terms of x and y. If we go to Cartesian form, rewrite them in terms of r and theta if we're going from Cartesian to polar. Okay. So the last thing for this particular section, I want to do graphing. And this one to give you an idea of all different kinds of curves that we'll discuss in this class. Now there's many of them, but we're just gonna kind of focus on certain three or maybe four in this case. Okay, so let me go back to my Desmos and I prep them to save a little bit of time on typing. Okay, so the first curve is 2 sine of theta minus 1. So I'm going to highlight it. Okay, and this curve, we're going to call it limacon. And I think it's something in French, if I'm not mistaken. It actually means like a snail. But don't quote me on that. I believe a few years ago. Um, is that heart? Heart is cardioid. So cardioid stands for heart, and it looks like a heart. Okay. So this one is limaçon. That is a French word for it. And again, don't quote me on this, but I think it means literally means snail. Okay. So that's one. It is a snail. There you go. Then the second one, that's a cardioid, right? Nope. I did not want to do that. Oh, I touched it with my finger. I don't know how to undo it, but okay. So now you kind of get an idea why it's called cardioid, right? For heart. Okay. And there are many different ways to have this heart oriented. And I think we're going to have a couple of problems next in the next section. We're going to try to compute the area that's bounded by this. Okay. Let's see. Then this one right here is a rose. So here we have 8 petal rose. And one of the projects that I've done with one of my students in Calculus 3, we investigated what controls the number of those petals. Okay, so you can play around with it and plug in different values for that argument. So let me just kind of give you a hint. What if I change this to something like 3? Now I have, well, it's going to update. There we go. There was a little bit of delay with projecting. So now I have a different number of curves, oh, of petals, right? Now, what if I put 6 in here? Okay, now it looks like this. So that argument inside the function controls how many petals my rose is going to have. Okay, we could also say, well, what's going to happen if we change the magnitude, right? So change the amplitude of sign. So let's say something like 2. And now maybe it's intuitive to you say, oh, of course, my petals get longer, right? Okay, so let's say I make it 4 and they get even longer. So if you were thinking about a honors project, let's say you're in honors college and you're in this class, those are the kind of things that I've done with my students. Now, that's not necessarily that what you want to do, but those are the things that we've looked into it, and it's kind of fun to look at it from a graphical perspective and then show it algebraically. Why does that work? Why does that happen, right? Okay, so that's our rows. And let's see, what else do we have? Here's another rose. So you can also use cosine here, right? And we have 5 petals, but it's rotated differently, right? Okay, look how it's not necessarily completely symmetric. Okay, so sine and cosine will generate different kind of roses. All right. Okay, so my recommendation for you as you work through homework, um, graph these, okay? Just get a good feel of what they look like. And one of the things it will be asking you to kind of match. So that's what I would suggest. Just use Desmos. You don't need to graph any of this stuff by hand. Plug it in into your Desmos and you will get the answer um, for your graph, okay? All right, so let me make a note here that we used Desmos to sketch these. Okay. All right, let's see. So before we do just a quick, very, very quick problem with the next section. I do want to get started with the next section because I don't want to I don't want us to fall behind because we're gonna have that one class missing. Do you guys have anything you would like to discuss before we go on? Anything at all? All good? All right. So I'm gonna go ahead and switch gears. I'm going to upload these notes after the class. Okay. And we're going to go ahead and start talking about calculus in polar coordinates. Okay, so one of the things that we will be now discussing is the area bounded by a polar curve. Okay, so let me kind of give you a quick reminder of what we've done in Calculus 2 when we said, okay, one of the first things that we discuss is an application of calculus or of integrals is we can find the area that's bounded by two curves, right? So here I'm giving you a quick sketch of what we've done in calculus 2. And I believe this is one of the very first topics we do. And we looked at that area right here, right? And we said, well, what is it? Okay, it's the integral from a to b of the difference, right? The difference is f1 minus f2. Think about it as top function and bottom function, right? So that's what we've done here. And we also did it for curves that were x a function of y, right? So something like this. Okay, and we've computed this area right here, where in this case, this curve right here was top. I'm going to put it in quotation marks. And this one was bottom, right? It's just a quick reminder of what we've done in Calculus 2. Now, similar idea is going to apply here, except that remember, we are now dealing with a different system, right? Not Cartesian system. I'm not going to go through the entire derivation. Maybe I'll mention it next time, just briefly, where this formula comes from. But the idea is here that it should kind of look similar to a formula for an area of a triangle, right? So if you remember area of a sector, right, that will kind of give you an idea where this formula comes from. But here we have 1/2 quantity f square of theta minus g square of theta. And that's going to be our main formula to apply when we're trying to determine the area bounded by a curve. Okay, so now let's go ahead and take a look at this problem. This is the first one. This is the only problem we'll do today. Okay, and kind of get you set up for next lecture, and then we'll go from there. Okay, so what is it asking us to compute? Find the area enclosed by one loop of the four-leaved rows R is equal to a cosine of 2 theta. Okay, so what I'm going to do here now, I'm going to determine what is my R1, F and G, right? So what are they? Okay, so you can think about it as your F is cosine of 2 theta, and your other function, that's just going to be 0 in this case. Okay, so if there is no other function, truly no other function, you can think about it as 0, because what are we really trying to compute? So let's say you wanted to compute the area over here, right? This area right here. Okay, I'm going to go ahead and highlight what I'm trying to show you. Okay, so the area of half a loop. Okay, and it's generated this way. Okay, if I start at r is equal, so theta is equal to 0. Okay, so theta is equal to 0. What happens? What do I get? I get r is equal to cosine of 2 times 0, which is cosine of 0, that's 1, right? So I do start at this point right here. This is my polar point, radius 1, angle 0, 0 radians, right? Okay, and as I increase my theta, it gets generated this way. Okay, now if I come over here, this intersection right here, I need to determine at which angle that curve crosses the origin. So one way to think about it is this. Well, where is cosine is equal to 0 for the first time, right? Because cosine is equal to 0 at several angles. Well, where is it equal to 0 for the first time? Well, let's set up our equation. Cosine 2 theta is equal to 0. one of the angles would be pi over 2, right? Okay, but we have 2 theta right here. So that means our theta is equal to pi over 4. Okay, and you can check, okay, if I were to do r is equal to cosine 2 times pi over 4, what do I get? I get cosine of pi over 2, so r is equal to 0. So that is the first time I'm crossing the origin. Okay, all right, so now we can think about it as r is equal to just 0, completely 0. That's going to be the second function. And if r is equal to 0, then I get my area, right? So my area of this curve right here. Now, if I compute this, I double it, and I get my entire area of one leaf. Okay? All right, so now let's go ahead and set this up. So a is equal then what? The integral, we go from 0 to pi over 4. And now I'm applying the formula 1/2. And what do we get here? This is cosine squared of 2 theta minus 0 squared d theta. Oh, I want to double it because this is me getting just half of it, right? So let's go ahead and double it. Well, that's nice because that cancels out, right? Okay, so this 2 and this 1/2 cancel out. And look, here's that cosine square again, right? So this is one of the reasons why I bring this up. It just pops up. It just does. So we go from 0 to pi over 4. Okay, this is cosine square of 2 theta. Let me go ahead and rewrite it already as 1 plus cosine of 4 theta, right? Cosine of 4 theta is equal to, over 2, okay, and d theta. Well, now we can integrate this. This is going to be 1/2. I'm going to factor, no, what we can just keep it as is 1/2 theta. And what happens here? This becomes sine of 4 theta over what? Over 8, right? Okay. We go from 0 to pi over 4. Okay. Let's see what we get. 1/2 times pi over 4, that's pi over 8. And then we get sine of pi, that's 0, minus sine of 0, all of that is 0. So we just get this nice answer, pi over 8. This is area, so that's units squared. Okay. All right. So I know this is a little bit rushed, okay? So I don't expect you to just kind of get it right away, right? We just started it, but I wanted you to kind of get that little bit of a head start of what we're going to be doing next time. Okay, we're going to be computing these areas, and I will explain in a little bit more details where that formula comes from, but you can kind of make that analogy with what we've done in calculus 2. We're computing the area between the two curves. Okay, and as you can see, we'll need to determine what those functions are, what the limits are, right? So depending on what we're asked to compute. Then once you set it up, most of that stuff is easy to compute. It's the setup usually that's a little bit tricky. Okay, I'm gonna go ahead and stop here. I'm gonna stop the recording, but I am not leaving and I'm not going anywhere yet unless you guys don't have any more questions. So let me go ahead and stop this.